All right, so tonight we're going to be going over Chapter 8, Sample Problems. I'm also going to assign some homework for Chapter 8. I'll be posting that. Well, actually, I'll just tell you what the homework problems are, and I'll post it later. Just get everything a little better. There we go. All right, so let's get to the ebook. And Chapter 8. All right, we need to get to page 247. Let's see if I can get there. One. We want to look at, start up with problem 8.3. Here, 8.3. In a simple random sample of 1,000 households, 150 households happen to own a barbecue grill. And it says, based on the characteristics of the population, the expected number of grill owners in the sample was 180. What are the values of pi, p, and n? Now in the book, remember pi represents the population portion, p represents the sample proportion, and n represents the sample size. So we'll just be consistent. We'll use that for the rest of the course. I think it's probably, instead of using something else which may confuse you. So first of all, what is n? What is the sample size in this case here?
150.
Okay. Sample size 150. Sure. Okay. Han, sample size.
I think 1,000.
1,000. Yes. Sample size.
Oh, sorry.
Simple random sample of 1,000. Okay, it's okay. Now in the simple random sample, it says 150 happen to own a grill. That has to be the sample proportion. Well, that's a sample number count. If we're going to convert that to a proportion, what is the sample proportion? Out of the, go ahead, I'm sorry, go ahead. I won't say anything. What is the sample proportion? That's P.
I didn't say anything. Did you say anything, Han?
No.
I heard, I must be hearing somebody's breath. But what is a proportion? Tell me what a proportion is. Maybe that would
15%.
Well, let's express it as a proportion, not as a percent.
150 over 1,000.
Yeah, which is equal to what?
0.15.
Yeah, that's the way we want to express it. All right, what's pi, the population proportion?
Oh, 0.18.
That's right. Because based on the characteristics of the population, right? Not on the sample, the expected number of grill owners is 180. So that's pi. That's what we're estimating to be the population proportion, 0.18. 180 divided by 1,000 is 0.18. All right, so you see, that's the way I want you to express proportions from this point forward in the rest of the course. I want you to express it as a decimal, right? Between 0 and 1. All right, 8.5. Now, 8.5 actually is just an exercise. Let's just go down to it. It's just an exercise in listing possible samples from a population. In this case, you know, you could get a little confused by what you're looking at here, but it really just means there are two possible values for this random variable, 1 and 2. All right. It's not even saying what it is, right? It's not describing what 1 and 2 measure. Nothing at all about it. So We just know X has two values, 1 and 2, and they both have equal probabilities of occurring. That's what that little table says. So the mean and standard deviation, easy to do, right? You simply multiply the values times the probabilities, and you get your mean. And you add up the products, you get your mean. And the standard deviation, you subtract. I think I've actually made a mistake here, what I did with the variance. Here, I actually gonna have to correct what I have in my answer sheet here. This is not correct. Well, actually it is correct. All right, I take that back. I did it correctly. And then the variance would be the square of the difference between each value and the mean. Now, what is the mean, by the way? It's pretty obvious what the mean is. Values are 1 and 2, and they're equally weighted. So what does the mean?
Is it
1.5.
Yeah, of course. It's just a simple average, right? They're equally weighted. All right, what's the standard deviation? Well, you have to calculate the variance first. So you take 1 and subtract 1.5 and square it. You take 2, subtract 1.5 and square it. And then multiply each one of those by the probability, which is 0.5. So when you do all that arithmetic, the variance comes out to 0.25. Okay? And then you take the square root of that, that's 0.5. So the square root of 0.25 is 0.5, that's your standard deviation. So our population mean is 0.25, 1.5, and the standard deviation is 0.5. And that sort of makes sense, doesn't it? If the there's only two values here. If the standard deviation is sort of the average distance from 1 to 2, well, the distance from 1 to 2 is 1, and then the average it, that's 0.5, right? I mean, it seems nothing remarkable about that. So that's what we have for the mean and standard deviation. Now it says here, for a sample size of 2. Now, in this case here, because we only have 2 values in the population, let's assume we have, we're randomly sampling from this population with replacement. All right, which means once we select one, we just put it right back. We could select basically the same item twice. All right. So let me stop sharing for here for a minute, and let's go to the solution page here, because the purpose of this again is just to show you how this all works. So here's your very simple population. Can't get any simpler than that, right? Here's your mean, here's your variance and standard deviation. Easy. They want to know what the now what they want here is a sample size 2. So I'm going to list all the samples of size 2. Have value of 1 for each one of those. You can have 2 for the first one, or 1 for the second, 1 for the first. 2. You see what I'm going? There's only 2 values, 1 and 2. So if you have sampling with replacement, because really the only way you can do this, I would think, you have 4 possible samples of size 2. I took the mean of these samples, right? I mean, take the mean of these, really easy. And then I figured out the probabilities of each one of those. It's just equally, right? Equally possible that you could have a 1/4 possibility for each of those 4. So they want you to list the sampling distribution. It's just these 3 values, right? The mean is either 1, 1.5, or 2, and here are the probabilities. Where did I get 0.5 from? I just added up these 2 middle values here, right? These 2 middle samples here have the same mean, and if I add up the probabilities, I get a half. All right, so there's my sampling distribution. Does that make sense?
Mm-hmm.
Really, really, really easy, right? I mean, this is, I think sometimes the easiest things are the most confusing. You're expecting more. But this is about as easy as you can get. This is your sampling distribution of the mean, sampling distribution of the sample means with the population of these 2 values. Now, what is the mean of the sample means, right? The mean, remember, the mean of the sample mean should be equal to the mean of the population, right? So to find the mean of these, the sampling distribution, again, we just simply multiplied each value times its probability and add up the products. And when we do that, we get 0.25 for the first product. The second product is 0.75, and the next one is 0.5, right? I believe. Am I not right about that? So you got 0.25 plus 0.75 is 1, plus 0.5 is 1.5. So there's your mean. So the mean of the sampling distribution is 1.5. If you took the variance of this, I bet you would get something smaller than the variance of 0.5, right? If you actually bothered, the problem doesn't ask for it, but if you wanted to find the variance and the standard deviation of this, it would be less than 0.5 for the standard deviation, okay? Then if you wanted to do a sampling distribution with 3, if you're sampling with replacement, you get 8 possible samples of size 3. Here they are right here. And here are the means for each of those samples with a 1/8 probability for each one of those. And then the sampling distribution would be, well, if the mean is 1, there's only one of those. So it's 1 out of 8, which is 0.125. There are 3 samples that have a mean of 1.333, which is 0.375. There's 3 of them that have 1.666 as the mean, and that probability is 0.375. And then you have, for a mean of 2, there's only one of those, which is 0.125. All right, and then if you simply multiply, now these numbers here, 1.333, 1.666, those are those are infinite decimals, right? They continue forever. All right, right? They continue forever. I probably should have put a 4 here, 1.334 and 1.667, but it doesn't matter. When you multiply these across, you're going to get the same mean of 1.5. It has to be. You're taking a sample from a population that has a mean of 1.5. The sampling distribution's mean must be 1.5, period. End of statement, right? You understand what I'm saying? The mean of this has to be 1.5. It just has to be. It has to be. Now, if we just kept everything as fractions here, you could see it would be 1.5, which is, what's 1.5? That's 6/5. No, that's not right. 1.5 is 3/2, right? 1.5 is 3/2. So if you found the mean of this, it would be 3/2 if you used fractions. But simply multiply these across and add them up, and you would get 1.5 as your mean. There might be some rounding error here a little bit. But that's the point. The point is the sampling distribution's mean is equal to the population mean. That's the purpose of doing this. Do you understand how to do that? If I ask you to create a chart like this, can you do it?
I think so.
Yeah, it's easy, right? Can't get any easier than this. Really, this project I can give to a middle school student, couldn't I? I could. Somebody in 8th grade, they could do this. It's easy. It's just, it's too simple, and therefore people think it's complicated. It's not complicated. It's really, really easy to do this. And once you create your sample, here's the deal. The sampling distribution typically has more values than the population does. There's more items. All right, because you're listing sample. I mean, here's a population of size 2, and you have how many different possible values of X bar? You have 4. The previous one, we had 3, right? We had 3 possible values. And as you get bigger and bigger samples, it's going to be much, much bigger than the population. All right, but this is called a sampling distribution, where the mean is the mean of the sample, this mean of the means. In this case, we're only dealing with means here. The mean of the means is going to be equal to the mean of the population, and the standard deviation is going to be a number smaller than the standard deviation of the population. And then we have that formula, sigma divided by the square root of n, for when we have very when we have very big populations, and the samples of less than 5% of the population. The sample size is less than 5% of the population. Then we can use that formula to calculate the standard deviation of the sample means. Right. So I wanted to show you this to you. It's not actually shown anywhere in the back of the book in terms of answers, but this is the way I would do it. And it will be posted. You can take a look at it and try it yourself just to make sure that you understand exactly what this is. All right. You have any questions about the sampling distributions? What they mean?
No.
Yeah. It's just a list of the means in this case, the list of the probabilities. And what I did here is just combine all the same means. All the samples had the same exact value for the mean, and added up their probabilities, and then created this little chart here, which is the sampling distribution. Obviously, for larger populations, the means are going to pretty much, most of them are going to be different from each other. So they're all going to be listed separately with their own probabilities. The probabilities, by the way, if it's a simple random sample, the whole idea of simple random samples is that the probability of each sample should be the same. The probability of selecting any of the samples should be the same probability. All right, that's the definition of a simple random sample. Any random sample, each individual in the population has the same probability of being selected, right? But as far as a sample, let's say here of size 3, each of these 8 possible samples of size 3, they all have the same probability of occurring if it's a simple random sample. All right. But in this case, a simple random sample with what? With replacement. Otherwise, we wouldn't have 1, 1, 1, right? But with this small population with only 1 and 2 as possible values, to illustrate this, we have to say with replacement. Otherwise, there's nothing to show, right? There's only one sample. There's only 2 possible samples, right? The first one is 1, the second one is 2, and the first one's 2, and the second one's 1. That would be it, and there's not much to show. But so we have to illustrate it this way with replacement. In an actual survey, they wouldn't be with replacement, right? We would be selecting somebody, and then once we're done with that person, they're removed from the population, right? They're not going to be sampled again. All right, let's go to 8.7, and this one's on page 253. So let's go back to the book. And just give me a second here. Book. 8.7. 8.7 is the next section. Let's see, 253, 254. This one. All right, here we go. All right. Now, they're saying here, Stephen Hahn, they're saying here that the random variable is normally distributed. Now, if they say that, what they mean is that the population is normally distributed. All right. So they're not telling you, they're giving you dollar signs here as if this is some sort of money variable, obviously, right? You see that. But they're not telling you exactly what it is, but they are saying that the random variable is normally distributed. So that means the population is normally distributed. Now, if here is the rule. If the population is normally distributed, the sampling distribution of sample means is automatically normally distributed for any sample size. You could have 2 or 3, it doesn't matter. If the population is normally distributed, the sampling distribution is normally distributed. Right? Once again, we could prove it mathematically, but we're not going to do that. All right, just assume that's true. So the mean here is $1,500. The standard deviation is $100. And they want you to determine the standard error of the sampling distribution of the mean for simple random samples with the following sample sizes. So let's define what they're asking for here. They say determine the standard error of the sampling distribution of the mean. What is the standard error? It is the standard deviation of the sampling distribution, which is equal to what? For a mean, it's equal to the population standard deviation divided by the square root of the sample size. So you see the word standard error, it's referring to the standard deviation of the sampling distribution of means, okay? Now, the purpose of this exercise is to inform you that as the sample size increases, the standard error decreases. That's the whole point of this exercise, all right? So I want you now to take a minute on your own and determine the standard error for each one of these. Shouldn't take you very long. Let's 2 minutes. Should be pretty quick. Answer this, come up with the numbers for A through D for 8.7. Some of these you could do through your head because of the square roots are, you're taking square roots of perfect squares, so you should be able to figure out some of these numbers. I think the last one you'll need a calculator for. That's D. So go ahead and do that, and then I will wait for your responses. Okay, I guess you're all done. Okay. So I'll switch back and forth. For A, Han, what is the standard error for A?
25.
Correct. And Steve, for B?
No?
I said yes.
10.
10, yes. I said that's
Oh, I
fine.
didn't hear you say anything either.
Oh, well, I said that's fine. And Steve, you're good too. And Han for C,
5.
and Steve for D. And round up to three decimal places for me for D.
3.162.
Great. So it's pretty easy to figure out the standard error, right? You just have to remember to do it. That's the that's the real trick, is to remember to divide by the square root of the sample size. A lot of students, they forget to do that. So I usually have to repeat this to students over and over again until they realize that, stop me from being so annoying, they have to actually give me the correct answer. All right, 8.9. Once again, it's for a random variable is normally distributed. Again, that's for the population. Mu, or the mean, is 80, and sigma is equal to 10. That's the standard deviation. Determine the probability that a simple random sample of 25 items will have a mean that is, now, in this case, all A, B, and C are all dealing with the same random sample. Now, what does this mean? What's the probability of random sample? That means if you take your population, right? And if you select out of the sampling distribution, right? If you select from the sampling distribution, a random sample of 25. All right, so you have a sampling distribution that has each one of the samples has 25 let's say people, we'll say they're people in population. 25 people are being selected for each random sample. All right, we're measuring the same thing, whatever mu is measuring, we're measuring that. And what we're saying here is, what if we select one of these samples, not a person, but a sample of size 25 out of the sampling distribution? What is the probability that that sample that we select has a mean that's greater than 78, or has a mean that's between 79 and 85, or has a mean that's less than 85? So go ahead and do that. Spend a few minutes, let's say 3 minutes here, to do this problem and come up with those 3 probabilities. Now you can use Excel if you like. If you ever, you can use Excel or you can use Minitab. In this case, I'm going to use Excel. I'm going to open up Excel. But you go ahead and go ahead and do that and take about 3-4 minutes. So I want you to get used to thinking about how to do these problems and what tools to use. There we go. All right, so let's see this one. Oops. I made the same mistake that most people make. I'm just talking to myself, don't mind me. So this is, I'm going to use Excel, but use, again, whatever you'd like. I'll tell you how it's done in Excel. Hey, my typing skills is really bad tonight. Very annoying. Something wrong. Still working or are you still working on it?
Yeah.
Yeah, go ahead.
I'm
Han, are
finished.
you done or you're done, Han?
Yes.
Okay. So
I'm not sure about my answers.
that's all right. That's not,
I might be done, but
you're not
I
sure
wanna-
about, yeah,
yeah, I'm not sure about my answer. I don't think that I have it, but
that's okay. That's okay. Don't worry about it. That's no problem. All right. Now, were you both using Excel?
yes.
All right, Han, you were too, Han?
Yes.
All
Yes.
right. Well, these are the three answers. I did it another way using a TI-83 84 calculator when I was writing the answers. It's very quick with the calculator, but Excel takes a little more typing. Now, the first one said, now, first of all, this is a normal distribution with a mean of 80. And actually, let me stop here for a second. Let's go back to the problem. The mean is 80, population standard deviation is 10, and the sample size is 25. That's what they're giving you. And the first probability, what's the probability that the sample mean is greater than 78? All right, now we're assuming a normal distribution. That means if the population is normal, that means the sampling distribution is normal. Okay. All right, so let's now go to Excel. Now this first one here is the probability greater than 78. Actually, I'm just going to put in here greater than 78. All right. And look at what I did. Now, greater than means with Excel, you would say 1 minus the normal function. The normal function is giving you the cumulative probability. That's a probability less than. So to get the greater than, you do 1 minus that. Okay. So 1 minus, and I would use the norm dot dist for normal distribution. You put in your value first, in this case 78. Put in your mean is 80. Now remember, this is coming from the sampling distribution. Since the population mean is 80, the sampling distribution mean is 80, right? It always matches. Now the standard deviation, again, it's very easy to forget to do this. You take your population standard deviation, 10, and divide by the square root. And in Excel, it's SQRT for square root of 25. And you put true as cumulative. That's what we want, cumulative. So 1 minus that is going to be 0.841 approximately. If we did 4 decimal places, it would be 0.8413. Now let me show you, this is of course how to do it in Excel. Let me just show you what I did using the solution, the calculator solution. What I did in this form here, I did 2 things. I showed you that X is normal. This is, remember that the symbols that we use for describing a normal. I said X, the random variable is, and I do this little wiggly thing here. And I said that's means distributed as, N for normal. And then in parentheses, I put my mean is 80, standard deviation 10. That's for the population. I said since sigma x bar, which is the standard error, is equal to 10 divided by the square root of 25, which is 2, right? 10 divided by 5 is 2. I said x bar is normally distributed, the mean of 80 and the standard deviation of 2. All right, this is my sampling distribution as a mean of 80 and standard deviation of 2, because that's the standard error. All right, 2. Now, I did this the long way. You don't have to do it this way. what I did was I converted, since this is a normal, X bar is a normal, I converted the X bar to a Z by using the Z formula. I took my 78 and subtracted the mean and divided by the standard error, not the standard deviation of the population, but the standard error, which is 2. So -2 divided by 2 is -1. Now this just becomes a simple Z with a mean of 0, standard deviation of 1, and I get 0.8413 when I calculate that, which matches what we did in Excel. Now you don't have to do it this way. I'm just showing you that once you establish that the sampling distribution has a mean of, is normal, has a mean of 80 and standard deviation of 2, then you can convert this X bar to what? A Z. Using this Z-score formula, and you get a corresponding probability with Z being -1. So this 78 represents -1 because this 78 is from a sampling distribution, all right? Notice if this problem was X, probability of X greater than 78, we'd get a different answer, wouldn't we? Because if X, instead of X bar is greater than 78, that means we're selecting one individual from the population. Therefore, we would have subtracted, to get the Z, we would have subtracted 80 and then divided by 10, right? And we would have gotten a Z of -0.2, negative. Is that right? Yes. I believe that's right. -2 divided by 10 would be -0.2. You get a different answer. You understand what I was just saying? This is the this is the probability of selecting a sample of size 25. If I said, what's the probability that X is greater than 78? Then I'm saying, what's the probability that one person selected from the population is a value greater than 78? And I would use 10 as my standard deviation because we're selecting one from a population. If I'm selecting a sample of size 25 from the population, then I'm dividing by the standard error instead of the standard deviation of the population. All right. I want to make that really clear so you understand the difference between those two. Again, many beginning students forget or confuse the two. And so we have to distinguish between, that's why I wrote it out this way, because I wanted you to see that this is the population and this is the sampling distribution. All right. And because I'm asking for X, the probability that X bar is greater than 78, I'm asking for you to use the sampling distribution to convert the 78 to a Z score. I'm asking you to use this, not this. All right. Does that make sense? This is the sampling distributions. This is the distribution of the sample means. Right. This is the distribution of the population values. Okay. Not if you understand what I'm saying, because this is really critical to understand this. That's why I'm spending a lot of time on this with you, because the rest of the course will become much easier for you if you know the distinction between this and this. This here is the population distribution of individual values in the population. What if we had 1 million people and we were measuring, what's 80 represent? I don't know, test score, some test score, all right? So we have a population of people who've taken this test, but we don't know what their scores are, all right? Maybe because the population includes people in the future, you know, who haven't taken it yet. This here represents what? A sample of size 25 of these people. All right. We're selecting 25 people from that population. What if we don't measure anything? What if we say, all right, before we measure anything, we determine their, their scores. What if we don't know their scores? What's the probability that the average for that sample is at least 78? All right, the average score of those 25 students is at least 78. That's what this question's asking. If I said, what's the probability that X is greater than 78, not X bar, then what I'm saying is, all right, I'm selecting one student from the population. What's the probability that that student scored at least a 78? That's a different question, isn't it? That question is asking about one student. Then I'm using the population because I'm selecting that person from the population. But if I'm saying I'm selecting a sample of size 25, where am I selecting that from? Am I selecting it from the population? Well, yes, to create it, obviously. But what I'm saying is I'm really selecting that sample from a population of samples of size 25. That's a sampling distribution. I'm saying out of all those samples of 25, I happen to have selected this one. What's the probability that that sample mean of those 25 students, the samples mean of those 25 scores is at least 78? That's what this is asking. And that's why I'm using the sampling distribution to convert the X bar into a Z. Because I'm not really selecting that sample, that particular sample from the population. I mean, I am, but I'm really saying is I randomly select a sample size 25. Where am I selecting that sample 25 from? From the sampling distribution of sample means. I'm selecting one of them. What's the probability that the mean for that particular sample is at least 78? And that's what this problem is asking. All right? Because I will assure you that on the next test, I will ask questions like that, where you'll have to know the difference between one person being selected and a sample being selected. And you have to know which of these you're using. All right? Now I know some instructors who do the following because they know students get so confused with these formulas. They actually say, always use the X bar formula and consider that one person is a sample of size 1. All right? So the students don't have to be able to distinguish between the two. But I think for both of you, and also for Rose, who's listening, who's going to be listening, I think you do understand the difference between these two. I hope you do, because it does make a difference to understand the distinction. All right. Now B, notice what I'd have to do in both cases here, if I'm going to convert to a Z, is I have to convert both the 85 and the 79 to a Z, right? And then find the probabilities that Z is between these two, which is 0.6853. And then this one is the probability X bar is less than 85, and I convert that to a Z, and I get the same answer. Now, again, you don't have to convert to Z's. I'm just showing you all this work so that you can see what the Excel is doing behind the scenes, and what, if you have a TI-84 calculator, what the 84 calculator is doing behind the scenes. It's converting all these to Z's. All right. But you don't have to do that in Excel. All right. You just have to use that norm.dist function. And for the greater than 1, you just have to say 1 minus norm dist, because it's the dist is giving you the probability that's less than. So if you have a greater than problem, you just say 1 minus that. You need 2 norm distribution functions when you have this, where you put 85 for the first one minus the 79 for the second one. And then this one, it's just a normal one. Where it says less than, you just say norm distribution and just put 85 in. So let me just stop sharing this and go back to the Excel. Excel, here we go. You know, so this one here is greater than 78. Notice I put 1 minus the normal distribution. Just remember to put 10 divided by the square root of 25. Now, you know, I mean, if you want to, you know, if you're repeating the same equation over and over again, you could put, you know, a cell in for x, right? You could put where you just change the x. You can have another cell which is referring to the mean. You put the mean somewhere. You put your standard error somewhere, so you just have it there. And then you just simply, you know, change the numbers. That's all. So the first one is the greater than one. This is the between, right? Between 85 and 79. Okay. So the only thing you're changing is the first number in both of these. And notice again, you don't have to calculate 10 divided by the square root of 25. You can let Excel do it for you. You just simply, for the standard deviation, just put in 10 divided by the square root of 25. Just type it right in. Right? You don't have to do these calculations separately. Just type it right into the formula here. The last one is just 85, right? Less than or equal to 85. And these answers match what I did with a calculator in the answer sheet that I showed you just a minute ago. All right. Any questions? So one thing I could do here, I think, any questions? Okay. So what I'm going to do here is I'm going to put a greater than symbol here. I'm going to put I'm going to type in between here, and I'm going to put a less than symbol here. So these are the three cases, right? You have a greater than problem, you have a problem with between two values, and you have a less than problem. So I'm going to leave these formulas as they are. I'm going to repeat, and then what I'm going to do is over here, I guess, I'll put x, and I'll put the mean, and I'll put standard error. All right? Because that's what you need. You need x, you need the mean and standard error, right? So this cell here is what's going to change for each of these problems here. So I'm going to put, let's see.
78.
Yeah, I'll just put the first one 78 just because that was the first problem. The mean is going to be 80. And the standard error was 80. And the divided by the square root. I don't know if it'll work with without putting the equal sign. I don't know. Let's try it. 5. Might give me an error here. No, it's listing it as a.
Is it 10?
Now I have to put equal to. The reason, because the SQRT is, it considers that to be alpha count. So I have to put an equal sign here. There we go. All right. I'm sorry, it should be 10. Yeah, you're right. 10.
I think it should be 10 over.
That's right. Yes, you're right. I just corrected myself. You're right. It'd be 10 divided by square root of 25. So that's my standard error. All right. So what I'm going to be doing here is I'm going to refer to these cells, right? So this cell here is E3. So this here is going to be, I'm just going to put dollar signs here. Dollar sign E3. Put another dollar, just to make sure it's referring to that cell all the time. This cell here is going to be the mean is going to be F3, right? So dollar sign F, dollar sign 3. And then this here is going to be G3. This way I don't have to repeat this. So I'm going to put dollar sign G, dollar sign 3. All right. And And then what I'm going to do is I'm just going to do the same thing for this one here. Let me just think for a minute. I probably should make this like put an x1 and an x2 in here, right? Oops, didn't want to do that. Sorry. I should have two x's here. I should have one for I'll call this x1. I should have a second x just in case I need it. X2. Okay. So for this formula here, I'm just going to use x1. This one here, excuse me, well, I already did. This one here's the between one, right? So this is, what are the numbers here? 85 and 79. So I'll say this is 85. And this is 79. All right. What I'm doing is basically setting up the spreadsheet for these problems. So this one, so I'm going to put E3 here. All right. That one, I'm going to put again F3. And then the standard error is going to be G3. And this one, I'm going to put X2 here, right? X2. So that what is that? That's I3.
H.
H3, yes. Sorry. You are correct. H. And then again, these are the same, right? These are the same. So this is going to be F3. It's going to be G3. Okay. That looks good. And then the last one, again, it's going to look like the first one, right? Except it doesn't have one minus. So this is going to be E3. And this is going to be F3. And this is going to be G3. The reason I'm doing this is because we have some more problems to do, right? All right. So now we're set up. We can repeat using this for multiple problems. The only thing we have to change are these values of x, the mean, and standard deviation, right? We have the greater than formula, we have the between formula, we have the less than formula. So we can use this for our tests. You can even set this up before you take your test, right? You have your Excel spreadsheet ready to go. And the only thing you're going to be doing is changing these numbers. Now, you may decide to have you may make the decision if you want, have standard deviation in here, and then put your sample size in here, okay? So that you can use this also for what? You can use it for regular normal distribution problems where you're just selecting one person from the population. So if you want, we can do that also, right? We could change this and put, we could do that, although we're not going to do it here, but you could do that when you're setting up your test, your spreadsheet. You could put standard deviation in here for population standard deviation, and then you put your sample size in also, which actually I would recommend here, wouldn't it? Yeah, you know what? That would be better because the sample size is going to change from problem to problem. So let's do that. Let's put, right? So let's do that. Just take a second. Population, SD, standard deviation. So we're going to put 10 in here. It's going to change the numbers here, by the way, so don't freak out. Don't get upset. And then we're going to put N here as our sample size, and we're going to put 25 here, right? All right, so we're going to change each of these formulas, and then for the so for the, let's see, E3F3, for the G3 here, it would be G3 divided by square root. You want to do it this way. Actually, it might make sense. It might make sense. Square root of what? Square root of I3, right?
I3.
What's that? Is that I? I3. Did I do it right?
Yes.
E, F, and then G. All right, so that's G. 10 divided by 5 is 2. Why am I not getting, oh, why am I getting the wrong answer here?
Because you change the E3 to 85. If you change back to 78, you will get the
Oh,
answer.
right. 78, you're right. That's it. Okay. All right, so that's it then, right? That's it. We could have that formula. And then if we have, so we're actually, it might make sense in this case here, if we do have a question about one person being selected from population, we just replace the n with 1. It actually makes sense to do that here. That way we have one formula that we can use for any normal distribution question. We just, if it's selecting one person for the population, we just replace the, we just put 1 in for the n, right?
Mm-hmm.
And it should give us our answer. So actually with Excel, it might make sense to do that. So let me go ahead and do the same thing here before I oops. Here. And this same one over here. Remember to put your dollar signs in here, so it's referring to that cell, no matter where you are in the spreadsheet. All right. So if we, let's just make sure it works. So this one would have been 85. We'll put 85 here and 79. There it is, 0.685. And then the last one was 0.9938 at work also. Okay, it works.
Cool.
So let's actually test this out. Let's go to 8.11. Let's go to number 11 in the book. And let's look at number 11. So word problem, right? Now it's referring to exercise 810. It says, from the manufacturing plant discussed in 810. So let's just look at 810 really quickly. We have a manufacturing plant worked, employees worked on average 62 hours of overtime last year with a standard deviation of 15 hours. So that's your population, mean and standard deviation. Mu is 62, standard deviation 15, and a simple random sample of 36 employees is taken, all right? So that's your small n. So 62, 15, and 36. Let me just stop sharing just for a minute. 62, 15, and 36. Let's go back to our spreadsheet. Just set everything up, right? The mean is, what is it again? 62. Population standard deviation is 15. And the sample size is 36. All right. Now, let's look at the problem. Let's look at what problem we're being asked to Let's go to question 11, because it's referring to that same population. It says the union president and the human resources director jointly select a simple random sample of 36. All right, good. To engage in a discussion with regard to the company's work rules and overtime policies. What is the probability that the average number of overtime hours, this is for a randomly selected random sample, last year would have been less than 65 hours? That's the first question. All right. So that's the probability that X bar is less than 65. So let's go to our spreadsheet. Less than is this last one, right? This formula right here, right? And X, what is it, 65?
Yes.
So we replace this with 65, hit enter. And this last number is our answer, 0.8849. If we round the four, yeah, see how easy it is if you set this up? You just replace the value and you get your answer, right? Just set it up this way. All right, let's go back to the problem. All right, what's the next one that's being asked? Between 55 and 65. Between 65 and 55 and 65. All right, let's do share. So 65, and we're going to place X2 with 55. That's the between question, right? That's the answer there, 0.8824. That's the between question. Your answer. See how quick it is?
Mhm.
So setting it all up, I think, is a good idea for you guys, right? Instead of taking it problem by problem where you have to reinvent the wheel. If you're going to use Excel, might as well set it up like the way I have it set up here. And then you're just plugging the numbers and getting your answers. All right. Remember, my tests are multiple choice, right? You don't have to show me any work. So you just need to set up your spreadsheet if you're going to use a spreadsheet. All right, let's look at 19. Let's go to 19. Problem 19. It's on another page, right? Or is it on this one? It's on this one. All right, let's read through it. The average length of a hospital stay in general or community hospitals in the United States is 5.5 days. All right, so that's your mean. Assuming a population standard deviation of 2.5 and a simple random sample of 50. So we got 5.5, 2.5, and 50. Immediately I go to my spreadsheet. All right, I'm going to go to my spreadsheet immediately and plug in those numbers. All right, so my mean, this problem is 5.5. Doesn't even matter what the units are. Standard deviation is going to be 2.5. And the sample size is going to be 50. Okay. Let's see what question they're asking, which are the three cases they're asking for here. All right. They're only asking one probability question. What is the probability that the average length of stay for this group of patients will be no more than 6.5 days? No more means what? What's another way of saying no more?
Less than or equal to.
That's right. So that's a less than problem, right? 6.5, it's the less than problem. Oops. Let's do this right. All right, 6 point. There we go. So it's the probability of X is less than 6.5. So we're going to put 6.5 here. Remember, the less than problem is the last probability, 0.9977. 0.9977, right? Is that that's what they're asking for? Is that the right one? Is it greater than or
Yes.
less than? That's it, right? 0.9977. Yeah. I think I got this backwards in my, yeah. I have to, on in the solutions, I got something wrong in there. I have to change it. All right, so that's your answer, 0.9977. Now let's let's read the question again, because I want to bring up something that's important. When they told you about the mean and standard deviation for the average length of a hospital stay, is there anything here that says anything about the population, how it's distributed for this random variable? The random variable is the length of hospital stay, right? That's your random variable. It's in days, right? It's a time variable. Is there anything here that says whether this is a normal distribution or not?
No.
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 Well, why could I use a normal distribution in this problem? Why am I using it?
Why?
Yeah, that's what I'm asking you. Don't ask me. I know the answer.
Hmm.
So why can we use the normal distribution if they don't give us any information about how the random variables distributed? That was true also with the last problem too, one before that. They didn't give us any
Could you
information.
repeat that, please?
All right. They don't give you any information about the distribution of the length of hospital stays here. They just give you the mean and standard deviation. There's nothing mentioned about normal. Why can we use the normal distribution? That's my question to you.
Did you say in the last class that if we select a sample from no matter what distribution, the sample will be normal distribution? Did you mention that?
No, I didn't. I didn't mention that particular.
You did.
Not what you just said. I said something else.
Hmm.
Okay.
I think maybe you mean it another way, but
I thought that I remembered something similar, but maybe it wasn't that exact thing. But
think about, let me give you the hint. Central limit theorem. What's the central limit theorem say? It's described in chapter 8. You should read chapter 8 because it really gives you the theory behind the central limit theorem. But what does the central limit theorem state?
if a population is normally distributed, the sampling distribution of the mean will also be normal.
That's not the central limit theorem, though. Central limit theorem is saying something else. That just means you don't apply the central limit theorem, but the central limit theorem is saying something else.
The sampling distribution of the mean will be approximately normal for large samples and
Right.
will more closely approach the normal distribution as it gets bigger.
Right. And what is the typical minimum number of samples? What's the minimum sample size typically we use to determine what's called large? 30. What's the sample size in this case here?
Okay.
Yeah, 50? Bigger than 30. So we do not need to know. This is what the central limit theorem says, that if you have a distribution that is not normal. In this case, we have to assume not normal because they don't say it. We'll just assume not normal. You need a sample size of at least 30 for you to say the sampling distribution is approximately normal. Now the book goes through some, it does an okay job, but it goes through and shows you some graphs of populations that are skewed, but the sampling distribution ends up looking normal once we get at least up to 30 for the sample size. You'll start seeing it, the sampling distribution looking like a normal, even if the population's skewed. To go back to the previous problem, which was number 11, I think that was the one we worked on before, it was the same issue. Number 11 did not, I mean, if you go to 8.10, actually, where it describes it, it does not say that the population is normally distributed, but sample size is 36, which is greater than 30. So we can, again, it's the central limit theorem, and say the sampling distribution is approximately normal. Okay. Now, the reason I mention that to you, because the next question in this problem says, what if the sample size had been 8 patients instead of 50? What further assumptions would have been necessary in order to solve this problem? And what is the assumption that you would have had to make? Let me see if you really... Go ahead.
The population is normal distribution.
Right. To use, in this case, because the sample size is less than 30, you would have had to been told that the population distribution is normal. In other words, this variable, this random variable called length of hospital stay is normally distributed. Otherwise, we couldn't use the normal distribution to solve this problem. We wouldn't be able to use it. See what I'm saying?
Mm-hmm.
Yeah. So that's an important part of this course, is to understand the central limit theorem and why we can apply it in most cases, but we can in some cases. So if they had said, for example, that this length of hospital stays is right skewed, maybe severely right skewed, right? Because you have those unusually large number of cases, a small number of cases where people are in the hospital for a long time, right? But what if they said it was not normally distributed, but it was right skewed, and you had a sample size of 8? You can't really use the normal in this case here, in that case. You'd have to find some other way of estimating the probability. Maybe there's another way, but the normal distribution would not been enabled. You wouldn't have been able to use it. Okay. You need at least 30. That's why sample size is important, because then you don't have to worry about the population. Sometimes, most of the time, the population, we don't even know anything about the population in many cases, right? I think about the COVID, that this new virus, we're learning new stuff about it, right? So picture different random variables that we can come up with. We wouldn't know anything about it. We wouldn't know what the population mean and standard deviation might be for some variable related to COVID because it's brand new. So we're going to be working with what? Samples. We have to make sure the samples are large enough before we can make any determination. All right? Come up with probabilities. All right. So what we've done so far is look at problems related to means. The mean of the population, the mean of the sampling distribution of sample means. What if we were dealing with proportions instead of means? Right? So that would be the next section here. And I'm not going to keep you on for very much longer. I just want to, I don't want to, drain you and all your energy. Let's go to this next section. Oops, looks like I got logged out. So give me a second here. All right. Oh, stop it. Cengage. All right. So what I think I'm going to do, actually, I don't want to keep you on too long. We still have some more to go through. Actually, we only have, let me see if I got this right here. Three more questions. Do you want to stay on for another 10 minutes? Would that be okay? Or would you rather call it a night and we'll just continue next time?
I can do 10 more minutes, yes.
10 more minutes? 10 more minutes is okay? We can do it?
Mhm.
Well, let's go ahead and do it. That way we finish chapter 8. All right, again, I have to re-sign on here. Cengage didn't have this time limit on here. Kind of annoying. So let me see if, all right. Give me a second here, get this set up. All right, can you see this sample distribution of the proportion? Can you see it? All right, you can see it. All right, I just want to make sure. I didn't know if I lost it or not. Now remember what a proportion is, right? We're dealing where we have two cases. We have like a binomial type situation. We have two cases, and we're looking at the number of successes, right? Out of all the survey, we're just counting the number of successes, like a political poll. Count the number of people in the survey or in a poll, right, who favor a candidate, and then divide that by the number of people in the survey. We get a proportion. So that's what it is. The number of successes, which is, in a binomial, divided by the number of trials gives us our proportion. All right, that makes sense?
Mhm.
That's what they mean by proportion. So we're just counting and dividing by the total number of cases. And then the mean, if we went through the same exercises we did with the means of a random variable that's measured, right? Remember that exercise we did before where x is equal to 1, x is equal to 2, when you took the mean and all of that. We could do the same thing with proportions. All right, we could take random samples and find the number of successes in those samples, and what we would find is that the mean of the sampling distribution of proportions, of all the proportions of all, we list all the samples, we have the sample proportions, find the mean of those, we literally add up all the numbers and divide by the number of possible samples, we would find that would equal to the population proportion. So the mean of the sampling distribution of proportions is equal to the population proportion. All right? Does that make sense? Sort of? And the standard error is what? It's the square root of the population proportion times 1 minus the population proportion divided by the sample size, all inside the square root. That's our standard error formula. Okay. Here's our z-score conversion if you're going to use a z-score. It's p, which is the sample proportion minus the population proportion in the numerator, divided by the standard error, which is this formula right here. So the only thing that we need to do this type of problem is an estimate of the population proportion and the sample size. And then, of course, if we were going to do an actual probability, we would have to know what p is, right? The sample proportion. All right, any questions about the mean and standard deviation for a sampling distribution of proportions? The mean is going to be equal to pi, the population proportion. This is the mean of the sampling distribution, all right? Now, notice they put EP here. I would say mu p, right? Mu p. And then sigma p is going to be this formula right here. All right? That is your standard error formula. Now, the sampling, central limit theorem for proportions is different than for mean. Remember just a minute ago, I said that the sample size has to be at least 30, right? If we know nothing about the population, the sample size has to be at least 30. But when we are dealing with proportions, we have to use special formulas. And the formulas are n times pi, you multiply those two numbers, n times pi, and then you multiply n times 1 minus pi. If both of those products are greater than 5, then the sampling distribution is approximately normal. So it's not just n. When we're dealing with a sampling distribution of means, n has to be at least 30, right? 30 or minimum, 30 or more. That's not true for proportions. And the reason is because what if pi is a very small value, like 0.005 or 0.01 or something like that? Then n could be 30, and it may not, the normal distribution, it still would not look normal, the sampling distribution. You have to make sure that n times pi and n times 1 minus pi are both at least 5. And if they're both at least 5, when you multiply them, you get a approximately normal distribution for your sampling distribution. So I think let's do an example that makes sense to you. Let's go to 823. 823. So this is on page, I guess, 256. Number 23. All right. It says a simple random sample with n is equal to 300 is drawn from a binomial process in which pi is equal to 0.4. Determine the following probabilities for p, the proportion of successes. Now remember, p is for a sample of size 300. Okay? Good. Now remember, to determine whether you can use the normal distribution to answer these probability questions, n is not enough. You have to multiply n times pi and n times 1 minus pi. And both of those products have to be bigger than, or at least as big as 5. So n is 300 and pi is 0.4. So n times pi is 120. That's way bigger than 5, right? We're good. But we also have to calculate n times 1 minus pi. 1 minus pi is 0.6. N times 1 minus pi is 300 times 0.6, which is 180. That's also way bigger than 5. So yes, we can use the normal distribution in this case for the sampling distribution. I want to make sure that you understand what I just said. Do you understand what I just said? You want me to
Could you
say it
repeat it?
again? Yes. It's very important. You have to know this. That's why I want you to pay attention. N is 300 is not good enough. Because it's bigger than 30, not good enough with proportions. You have to multiply n times pi and n times 1 minus pi, and both of those products have to be at least 5. N times pi is 300 times 0.4. That's 120. N times 1 minus pi is 300 times 0.6. That's 180. They're both bigger than 5, so we can use the normal approximation for the sampling distribution. You have to remember, this is a binomial process. This is a discrete distribution. We're using a continuous random variable to approximate a discrete distribution. We're using the normal distribution as an approximation for something that's discrete. You see what I'm saying?
I think so.
I want to make sure you say not I think so, I know so. Do you know so? And the reason I'm saying that, Steve, is because the discrete, this is a discrete process. Binomial is discrete. We're counting. There's no 1.2 or 1.3 or 1.75 for values. It's 1, 2, 3. We're counting people. We're counting things, right? The number of successes. There's no, they're all whole numbers. So this is discrete. This binomial is discrete. We're using the normal distribution, which is continuous, to approximate a discrete process. So to do that, we need a special formula to do that. And that's the n times pi, n times 1 minus pi. The central limit theorem doesn't apply here in the way it's described. That's only for means. Because we are not approximate. It is never true that a binomial is normal. Because it's binomial. Binomial is binomial. What we're doing here is, if n times pi and n times 1 minus pi, if those numbers are big enough, then we can use the normal to approximate the binomial probabilities. Now, you may ask, Steve and Han, you may ask me, why bother doing that? If we know how to calculate binomial probabilities, which we do, right? Why do we need to do a normal approximation, right? Legitimate question, right? Why bother doing all this? I know how to calculate binomials, right? We did that. Why do we have to bother with this nonsense? The reason is because starting next week, we're going to be talking about estimating parameters like the population proportion, estimating and doing hypothesis testing. All those things that we'll be doing next week, starting next week, require the normal distribution. They require the normal distribution. That's why. So we need the normal distribution to be used in this case for the inference that we're going to be using later. Otherwise, it's going to be very difficult to do inference. All right. So just take my word for it, that the normal distribution is required to do inference. That's why we're doing this normal approximation for a binomial. So part A here says, what's the probability that if we select a sample of size 300, what's the probability that the proportion of the 300 is at least 0.35? Okay. Now, what does that mean? Well, what's 35% of 300? 105? Is that 105? What we're really asking for, what's the probability that we get at least 105 successes for the 300 repetitions of this process? That's what we're asking. That's what 0.35 means. It means 35% of 300, which is 105. So we're really asking, if we have 300 repetitions of an experiment, what's the probability that we get at least 105 successes? That's how we would answer the question if we were doing the binomial, right? But in this case, we're doing a normal approximation. So what we need to do, Steve and Han, is we need to convert the P into a Z. And that's what our calculator is going to do. However, with Excel, we don't really need to do that. So this is what we're going to do. Let's go to Excel. I'm going to just show you one of these cases here. Actually, but I think you're going to be able to do 25 and 27 on your own, but maybe next time I could show it to you. Let's just look at how to set up Excel for this, and then I'll call it a night. Let's just go somewhere else on the spreadsheet, okay? We have the same situation. We have, actually, let's just set it up down here.
We didn't see the Excel.
What's that? Oh, you can't see Excel.
We're not seeing.
No, no,
we're
I know.
not seeing.
You're not seeing it, yeah. Yeah, it's getting a little late for me also. All right. I think we could use the same formulas as before, but we're going to have a different, we're let me think about, no, not the same form as, yeah, we're going to use the normal, but we're going to use for the x, we're going to use p. We'll put p here. All right, that's our sample proportion, p. We're going to put the mean in as pi. So I'm just going to type in pi for pi, pi for pi. Just know that's the population proportion. And what else do we need? We need n, right? N. So this is for the proportion problem here. So let me think about this for a minute. All right, so let's do greater than. Let's do between. And let's do less than. So normal, right? We're going to say normal, NORM, and then we'll use the normal distribution. Now, the value is still going to be E, what is this? E7, right? That's where the P is going to be. So we'll say E7. So 7, okay, comma. And then we need our pi. That's our mean. That's going to be F7. And our standard deviation is going to be the square root. We'll do square root. And it's going to be pi, which is what? Pi is going to be F7. Times 1 minus F7, in parentheses, 1 minus F7, divided by, where's N? G7. Close parentheses, and then close parentheses again. Enter too many arguments. Okay, what did I do wrong here? So let's see. Oh, I only need one of these, I think. Square root. All right. And then let's see. Square root. This does that. And then do I have too many arguments? I don't think I do. F7 times 1 minus F7 divided by G7. Close it, and then I close it again. Why is this too many arguments? Oh, I forgot true, right? I forgot to say true. So I'm going to type in true. There we go. Now, why it's giving me an error here is because I'm dividing by a number that's not there, right? So let's do a greater than question. Let me see if I can find one. What's the probability that P is greater than, all right. N is 300. Let's type in the number 300. This question is saying 300 is N. And pi is 0.4. And we want to know the probability that N, P is greater than or equal to 0.35. We'll put 0.35 here. There's your answer. But it's greater than, right? Mm-hmm. So what did I forget? 1 minus this, right? 1 minus it. 1 minus. That's my answer. That's a greater than question. 1 minus. That's the answer. The only thing you need for proportion problems is your population estimate, your sample estimate for pi, and then the sample size, and that's it. You have to set up the formula correctly. But you use the same normal distribution function in Excel. Get the same answer that way. All right? So you do have to list it separately. So you could, you could say, you could type in mean here, and then down here, you would say, proportion. That way, you know that these set of formulas are for the mean questions, and this set of formulas here are going to be for the proportion questions. Okay? All right, you have any questions about that? Does that sort of make sense what I just did? I know it's very late. We
Yes.
should stop, but do you understand what I just did? The formula
Yes.
what's different here is the formula for the standard error. It's the square root of pi times 1 minus pi divided by n. So you have to set up that formula inside where you have the standard deviation, where the standard deviation position is. You have to put that square root right there. And then the mean is going to be what pi is, what the population estimate is. And the first number is going to be what you're going to use for the probability question. That's what the first one here is. I just said P, which is what you're really asking. What's the probability that the sample proportion is at least 0.35? So that's why I put P here. So what we're going to do, I think, is spend maybe 15 minutes at the beginning of the next session finishing this up. I want to make sure you feel comfortable with this. I'm not going to assign the homework for this yet. All right, so let's wait. And let's spend 15, 20 minutes next time going over this again. The proportion part. I think the mean part you understand pretty well. Do you have a good understanding? All right, but the proportion is a little fuzzy because it's late and we're doing it last. So why don't we spend the first part of the next session on finishing this up and maybe doing the other couple problems. And then I'll introduce the next topic, which is chapter 9 on confidence intervals. I'll start, it's an application of what we're doing anyway. So it'll be easy to switch to that. All right. But I don't want you to feel stressed out with this, what I just went over here. So take it easy. I would read chapter 8. If you can, if you have some time, go through chapter 8. And then we will continue with 8.23. I want to do 8.25, 8.27. It may take longer than 20 minutes. Let's say it'll take half of our period, all right? Half of the time. And then I'll introduce you to chapter 9 next time. Now, our schedule, let me just tell you the schedule. I'll stop sharing here so we'll do this next time. I have posted a quiz which covers chapters 5 and 6. I posted it, and it's going to be due on Friday at 11:59. I'm giving you 3 days to complete the quiz. It's just, there's some calculations in there, but they're short calculations, and there's some definitions. Chapters 5 and 6. All right, probability, discrete probability. All right. So 25-minute quiz to complete by Friday. Once we're complete chapter 8, then I will give you the next quiz number 4, which will be due on Sunday at 11:59. That will cover chapters 7 and 8. Quiz. So short calculations, just like the ones we did so far. Maybe you forgot about the quizzes, but remember there was 5 questions, 4 points each, that sort of thing. Fill in the blanks. All right, I'll set it up.
Is the quiz still filling the blanks?
Yes. Yes.
Okay.
Yes. So you're going to have a calculator by you because there's some short calculations with these also, but not long ones. Short.
Okay.
25 minutes for each quiz. So the quiz I have out right now, it's actually posted. You'll see it. It's due on Friday, 11:59. So Rose, if you're hearing this, make sure you complete that. All right. And then the next quiz I will post it on Thursday. It'll be due on Sunday at 11:59. Okay. Now, how about your next test? The next test will cover, I've just made this decision today. It will cover chapters 5, 6, 7, and 8. So it's going to cover probability, discrete probabilities, binomial, hypergeometric, Poisson. It'll cover normal. It'll cover chapter 8 on the sampling distribution problems we just did. That will be due. I will post that. We'll try. I mean, I don't know if I'll get it done, but I'll try to get it done by Sunday evening, late Sunday evening. And that will be due next Thursday, not this Thursday, but next Thursday at 11:59. Because last time I remember when I did the last test with you guys, if I'm not mistaken, I tried to get, I would really rush to try to get it done before the weekend, but none of you worked on it at all during the weekend, which is fine. You want to have fun during the weekend. So I'm not going to do that this time. I'm going to take my time. I'll have it. I'm going to try to post it by Sunday evening before I go to sleep. Test number 2. And it will be due Thursday at 11:59. All right. Give you 3 days to complete the test. And it will be 90 minutes long. Same number of questions, 22 questions, multiple choice, and 90 minutes long. Okay. And that will cover everything through chapter 8. All right, so that's, I think logically that makes a lot of sense. So do work on quiz number 3. That's all you need to work on for Friday. And then when we come back on Thursday, I'll give you some, we'll talk about the next quiz after that and then the test, all right? But I want to give you a heads up about what the schedule is going to be like. Any questions about any of that? Sound all right? Yeah, I'm trying to give you adequate time. Go ahead.
Will we have a short video like last time for the test?
Yes. Yes, I'll go over, yes. Give you a short video on the test, yes.
Thank you.
You're welcome. All right, guys. So anyway, I'm going to stop the recording.